Hey guys, so this is the lecture from Tuesday before spring break. There were a number of people absent from that lecture, so I figure I will just post all the magnetism lectures. So everything from here on forward is exam 3 material. Nothing that is posted on YouTube will be covered on exam 2. So before I talk about magnetism, I first want to talk about electric fields. We've been working with electric fields for a while, so there's a few things about electric fields I really want to emphasize. So in chapter 16, we introduced the idea of the electric field. We introduced the idea of forces existing between electric charges. So we kind of could think of electric fields as these things that are created by electric charges. In a sense, the charge is the source of an electric field. So I could say charge QA creates an electric field EA. Charge QB will see the electric field created by charge A. And then charge B will feel a force on itself equal to the electric field created by A times however much charge that particle has. So the force on B is QB times the electric field created by EA. Now, if I plug in KQA over R squared for EA, the electric field created by point particle EA, I end up just mathematically identical to Coulomb's law. But I like to write the electric force written in this form because this is more general. I say the force on charge B is equal to the amount of charge particle B contains multiplied by the electric field at the location of particle B. Now there is a value for electric field at every location in space, but I don't care about the value of the electric field at every location in space. I only care about the electric field at the location of charge B. And that electric field might be created by one particle, it might be created by a million particles. Regardless of which scenario I'm in, I still have the same relationship between the force on particle B is the charge of particle B times the electric field created by everything else. So the electric field is a quantity that exists everywhere. So there in this picture, there's an electric field here, there's an electric field here, there's an electric field here, there's an electric field at every location in this picture. And the electric field will exist whether or not we place a test charge, in this case QB, to see it. The electric field still will exist everywhere. Now, notice from the above equation, if QB is a positive number, the force is going to be parallel with electric field direction. If QB is a negative number, the force will be anti-parallel with the electric field direction. So the direction of the force will depend on whether or not we are placing a positive test charge or a negative test charge somewhere. Now, the electric field is a vector field, so that means it has both a magnitude and a direction at every location in space. Now, that value could change. If I'm close to a charge, I might have a really strong electric field. If I'm far away from a charge, I might have a weak electric field. But regardless, I still have a notion of direction and magnitude at every location in space. Now, when I draw an electric field, I draw arrows on a piece of paper. What I'm doing is I'm trying to take a pen and paper and I'm trying to find a way to pictorially represent this physical quantity that is the electric field. So what I do is I draw arrows. Arrows are useful for signifying a direction. And if the arrows are all really packed tightly together, that implies I have a high density of arrows. I have a stronger electric field around here. Now, there isn't actually anything moving in this picture. Just because I draw an arrow doesn't necessarily mean motion. If you think back to Physics 121, we said the acceleration due to Earth's gravity is 9.8 downward. So the direction of the acceleration at every location in the room is 9.8 downward. Now, that is different from saying, is something moving and accelerating downward at 9.8? Well, no, there is not a particle accelerating downward at every location in the room I'm sitting in, but the acceleration due to gravity still is 9.8 downward at every location in my room. So just because there's a particle there, or I'm sorry, whether or not there's a particle at every location, there's still an electric field at every location. So if I ask you what is the electric field at this location right here, you don't ask about what is the force between all these four particles. You say the red particle will create an electric field at that location. I use KQ1 over R squared to find it. The green particle will create an electric field over there. I would say KQ2 over R squared. The blue and the yellow particle each create their own electric field there. KQ3 over R squared, KQ4 over R squared. And then I write the direction. If it's a complicated 2D problem, I might need to incorporate trigonometry for vectors and components, all that stuff. But every particle contributes to the electric field at this location, and I just add up all those contributions, those four vectors. So a value of 0 is a valid, is allowed to be the value of an electric field at a certain location. Now, in general, we prefer to use nice homogeneous electric fields that are constant in time, something like this. It's just easier to work with mathematically. There's no reason we're required to use this, but this electric field would be kind of a mess because we have vectors in a bunch of different directions. Here, the math of working with this electric field is easier, so we end up usually using something like this. Now, we also talked about the notion of electric flux. So flux, in its purest sense, is an idea from mathematics. You could always take any vector field. I think this is covered in multivariable calculus in Niagara University. I think that's Calc 3. So you take any vector field and place a surface in that vector field. So here's a vector field on a sheet of paper I drew. I could draw a surface something like this. And then I could say, okay, how much of that vector field passes through my surface? And that is the flux through the surface. So a surface is an idea from math. A vector field is an idea from math. A flux is an idea from math. When I say electric flux, I'm now just taking an actual physical thing and ascribing reality to that. And I use the tools of mathematics to describe electric flux. So basically, set up a surface in a vector field. There are arrows at every location in space. And just ask how many of these vector field arrows pass through my surface. And that's your flux through the surface. Now, the existence of electric fields means we can meaningfully talk about electric flux. And electric flux is formally defined as EA cosine theta that we talked about before. And this is flux through any surface. So this is what is electric flux. Now, if I consider a closed surface, so let's take a surface with a notion of inside and outside the surface, whether or not there is an electric flux passing through the surface, a net electric flux, so I think of that as an arrow going in could be canceled by an arrow exiting. But if I have more arrows exiting, I could infer I have a positive charge inside my surface. And if I have more arrows entering, I could infer I have negative charge inside my surface. So if I have a closed surface, I could say the electric field arrows passing through the surface, either into or out of, is directly related to the charge inside that surface. So do the field lines more exit through the surface? That means I have a positive charge. Do field lines enter my surface? That means I have a negative charge. And the total amount of flux through that surface is equal to the total charge inside that surface, divided by a constant of nature that we just throw in a calculator. So this is just a quick summary. Refer to previous slides for more in-depth discussion of electric flux, electric fields, and all that. So I am going to stop the video here, and I will begin talking about magnetic fields in the next video.